Sometimes, even big discoveries can seem pretty modest at the time. You may have a tough time even guessing what this picture is. It was sketched by hand over 400 years ago. The author even admitted that he had no idea what he was seeing, but it was definitely unusual. The author was Galileo, the father of modern astronomy, and his sketch is the planet Saturn and its rings. From this view, he thought that Saturn was not one object, but three. A large planet in the middle, and two large nearby bodies. One precedes and one follows it in the planet's orbit. At other times, he thought the planet had two handles attached to it. We can forgive him for his confusion when we consider that his observations were made with one of the first telescopes ever built. By today's standards, the lenses in his telescope were of extremely poor quality. It took another 45 years for telescopes to improve to the point that Dutch astronomer Christian Huygens was able to recognize that Saturn was in fact surrounded by rings. Even today, Earthbound telescopes have trouble seeing Saturn in great detail because of the turbulence in Earth's atmosphere. When viewed through telescopes, images shimmer and shake because we are looking through a boiling pot of air. Pockets of warm air rise, while cooler, denser pockets fall. Air deflects the light from distant stars and planets before it even reaches the telescope. It is very much like looking at objects that are at the bottom of an agitated swimming pool. A video camera can record dozens of images each second. Computer software can then be used to sort them, finding the ones that look the sharpest. This might only be a few dozen out of the thousands of initial images. The best ones are then combined, forming an improved image. Applying this technique to views of Saturn, we can see that the rings are not uniformly bright. The inner and outer regions are dimmer than the center, and there is what appears to be a dark break in the rings. This area, called the Cassini division, is wider than the United States. For many years, images like this convinced astronomers that there were just 3 rings. The part outside the Cassini division was called the A ring, and just inside is the bright B ring. Much closer to Saturn is the faint C ring. The Hubble Space Telescope orbits Earth outside of our atmosphere. As a result, its images are exceptionally sharp and clear. Hubble shows us that Saturn's rings are more complex and interesting than we ever imagined. There are not just 3 rings, there are actually many rings that make up the entire system. The main rings are over 150,000 miles in diameter, yet in most places they can be as thin as 30 feet. If you tried to make a scale model of the rings using a sheet of notebook paper, it would need to be 1,000 times thinner in order to be correct. While the rings may look like solid structures in these pictures, they actually contain many trillions of pieces of frozen water and trace amounts of rock. Their icy nature explains why the rings are so bright, even when viewed from Earth. They sparkle in the light of the sun. By bouncing radar signals off the rings, we find that the ring particles range in size from specks to icebergs the size of small houses. We can even spot the occasional background star through parts of the rings. But even with our best telescopes and space probes, these particles are too small to be clearly seen in any pictures. Each ring particle speeds around the planet like a miniature moon, going about 50,000 miles per hour. To help understand why they do this, imagine swinging a ball on a string around your head. The ball follows a circular path due to a force called tension that is exerted by the string on the ball, even though it is being pulled outward by the centrifugal force. For orbiting objects, it is the force of gravity, not tension of a string, that makes them orbit Saturn. Orbiting is a balance between the force of gravity pulling bodies inward and the centrifugal force pulling each away from Saturn. Without the force of gravity, they would escape into space. While Saturn is likely to be over 4.5 billion years old, it is still unknown when and how the rings actually formed. One theory is that the rings once made up one of Saturn's moons. What would have caused this moon to break apart? One explanation says that Saturn's own gravity may be the culprit. The amount of gravity that an orbiting moon feels depends on its distance from the planet and on the planet's mass. The side of the moon that is closer to the planet is a shorter distance away, and is therefore pulled harder than the far side. This force difference, called the tidal force, is normally small. But if the moon gets too close to the planet, the tidal force will become so large that the moon will be torn apart. The area where this can happen is called the Roche limit. Long ago, an icy moon or comet could have been torn apart inside this Roche limit. Ice from the moon's exterior formed Saturn's rings, while the rocky interior eventually fell into the planet. How far back in time could this have happened? We study the rings themselves to figure this out. The icy ring particles are expected to darken over time due to dust from impacts with small, rocky meteorites. Yet most of Saturn's rings are bright and very reflective in the sunlight. This led us to think that the rings were formed recently, in the last 100 million years or so. However, the brightness seen in the rings depends on how much matter is actually there. We now know the rings are more massive than previously thought, 3 times more actually. The pollution from dust will not be as apparent when it's spread over more pieces of ice. All of the ice particles interact in this dense environment, colliding with each other to form clumps or breaking others apart, exposing bright new faces of ice. This recycling throughout the years could date back to the formation of Saturn itself. In the early 1980s, the Voyager spacecrafts visited Saturn on their way out to the outer solar system. They found that the Cassini division, once thought to be empty, is filled with particles. Another of Voyager's discoveries was the existence of new rings, not just the A, B, and C rings seen before. We now know there are over 7 in total, and each is composed of thousands of sharp and narrow ringlets. Some are bright, while others are dark, depending on how much material is in each. While passing by Saturn, Voyager showed us that there was still much to learn about the planet and its rings. In 1997, the Cassini-Huygens spacecraft, built by NASA, the European Space Agency, and the Italian Space Agency, was launched. En route to Saturn, the 22-foot-tall probe passed by Venus twice before flying by Earth and Jupiter. Each flyby accelerated Cassini, allowing it to reach Saturn. 7 years later, after traveling billions of miles, it joined over 60 moons and the ring material in orbit around Saturn. As the second largest planet in our solar system, it is 9 times wider than the Earth. Saturn rotates so fast that it bulges at the equator. This oblateness forces ring particles and inner moons to revolve above its equator, where the effect of gravity is strongest. With false color imaging, Cassini's camera captures storms in Saturn's atmosphere. Lightning storms on Saturn are marked by bluish spots like the one seen here. This flash is 100 miles in diameter and produced about 3 billion watts over the course of 1 second. Perhaps the strangest feature in Saturn's atmosphere can be found at the North Pole. Each side of this hexagon pattern is wider than Earth. It was first seen in 1980 by Voyager 1 and is still puzzling scientists today. Images taken over time show us that the hexagon is nearly stationary, while the rest of Saturn's atmosphere moves around it. By simulating the atmosphere of Saturn in laboratories, scientists have been able to recreate this unusual structure. They have found that it is probably formed by a narrow rivulet of air, similar to jet streams here on Earth. Ammonia ice clouds are forced out of the way as they pass. When viewed in infrared light, we see that the hexagon extends at least 47 miles into the Saturnian atmosphere. From the vantage point of Cassini's orbit around Saturn, the complex nature of the rings can be seen and studied up close for long periods of time. One of the first things Cassini looked for in Saturn's rings were these strange features. First seen by Voyager 1, these so-called spokes sometimes appear dark, while other times seem bright. They consist of very small particles that travel around Saturn, going faster than the rings rotate. It may be dust produced by the impact of marble-sized meteoroids with the ring particles. The dust has a static charge, and it is suspended above the rings by electrostatic forces. The motion of the dust seems to be controlled by Saturn's magnetic field. As Saturn orbits the Sun, it travels much slower than the Earth. Because of this, and because Saturn's axis is slightly tilted, we see it from different angles. This allows us to view the rings from top and bottom, and even edge-on, when they seem to disappear. Twice during Saturn's almost 30 Earth-year orbit, the edge of the rings are aimed directly at the Sun. At these times, Cassini sees the rings take on a different appearance as sunlight scatters throughout them. Rays of sunlight skim along the upper and lower surfaces of the rings, making any tall features noticeable. When we look at the outer edge of the B ring, the densest and most massive ring, we find vertical structures casting long shadows. These peaks tower more than 1.5 miles above the ring plane and stretch for 750 miles. This is quite amazing when you consider that the ring's thickness varies by usually only 30 feet. What could have caused these peaks to form? As ring particles orbit around Saturn, they sometimes collide and stick together. Large clumps called moonlets are created. It is thought that moonlets, 0.5 mile in size or larger, force the ring particles upward to form these towering peaks. Moonlets are usually too small to be seen with Cassini. However, their effects are visible. One moonlet created this propeller-shaped peak in the A ring. It is 80 miles long and 650 feet high. These features allow us to track the orbits of moonlets for the first time ever. When we look at the rings, we find the occasional gap, like the Keeler gap in the A ring. In 2005, Cassini's camera discovered a small moon orbiting Saturn in this particle-free region. Gaps in the rings are kept clear by moons forcing particles out of their path. Particles at the edges of the Keeler gap, seen here, are elevated to heights 150 times higher than the ring is thick. Many other features caused by the planet's moons and moonlets can be studied throughout the Saturnian year. What you're seeing are spiral density waves found in the A ring. These patterns are produced when dense, bright areas alternate with less dense, dark areas in the rings. It is theorized that these density waves are formed similarly to how the spiral arms seen in galaxies are created. The gravitational attraction of stars, not moons or moonlets, form the spiral arms. When we study the moonlets and the effect they have on the rings, we start to understand that the physical processes we see are very similar to those associated with planetary formation. Billions of years ago, a young sun was surrounded by a disk of gas and dust. Saturn and its rings make up a natural laboratory that resembles what this early solar system might have looked like. We know that particles found in the rings and those that would have existed in a young solar system are too small to attract other particles by the force of gravity. They are instead attracted by electrostatic forces, clumping together to form larger bodies. This electrostatic attraction has been proven to occur in the microgravity environment of the International Space Station. In this video, sodium chloride crystals form clusters in a matter of 10 seconds. These experiments have shown that small grains form clumps which can grow larger, eventually pulling more material in by the force of gravity. These would gradually go on to form the planets and the moons in our solar system we see today. Ring particles bump into each other, causing rings to spread with time, yet the F-ring remains remarkably narrow. This is due to the two small moons, Prometheus and Pandora. Pandora orbits just outside this ring, while Prometheus orbits inside it. They are called shepherd moons because they herd the ring particles, keeping the ring narrow. To understand this process, first know that objects closer to Saturn have less energy than objects farther away. This means that if a ring particle were to slow down or lose energy for any reason, it will spiral closer to the planet, and if it should speed up or gain energy, it will spiral outward. Say that a ring particle gets bumped by a neighbor so that it begins to spiral inward toward the planet. The faster inner moon passes by and gravitationally drags the ring particle, speeding it up. The particle, now having more energy, spirals back into the ring. If, on the other hand, a ring particle gains speed after a bump, it will spiral outward, but the slower outer moon gravitationally pulls the particle and slows it down, decreasing the particle's energy. The narrow ringlets we see throughout the rings may be due to small shepherd moons embedded within them, too small to be seen in our images. Images taken by Voyager 1 first revealed the F-ring's complex, seemingly braided structure. As Cassini orbits Saturn, it observes these unusual features up close and sees that it is constantly changing its appearance. Kinks and channels appear when the shepherd moons and smaller moonlets interact with the ring. During its orbit, the inner moon Prometheus gets close enough to the F-ring that it draws out a streamer of material. The streamer trails behind Prometheus because the material in the F-ring orbits slower. This happens once every orbit of Prometheus, creating a new streamer ahead of the previous one. Streamers get longer and darker over time, forming channels. This mosaic shows how one evolves over the course of an hour. Small fans are seen to form within them. Some material is forced together, forming moonlets large enough to cast narrow shadows. The channels dissipate over time, and the moonlets created in them may be destroyed when Prometheus passes again. On the other hand, they may survive and grow larger as Prometheus forces particles its way. These moonlets may be the cause of trails seen in the F-ring. They pull material out of the ring as they pass through it at 4 miles per hour. Cassini captures one breaking apart as it travels through the core of the F-ring. In 2006, the Cassini spacecraft captured this remarkable image of Saturn eclipsing the Sun. Even though this is the night side of the planet, it is still illuminated by light reflecting off the rings. Just above the main rings is a small bluish object. What you see is not a moon. It is much farther away than that. It is planet Earth, seen from roughly 750 million miles away. From this view, we see that there are 2 additional rings of Saturn. Outside the A and F ring is the dim G ring, and farther out still is the extremely wide and diffuse E ring. It is made of very fine ice particles, more like ice dust. They are easily dispersed by micrometeorite impacts and by the planet's magnetic field. These processes accelerate the particles into space. Therefore, there must be something replacing this lost ice. When we look inside the E-ring, we find the source. Saturn's moon, Enceladus, just over 300 miles across, has relatively few impact craters on its icy surface. Since meteor strikes are common, there must be some way in which the impact craters get erased over time. This tells us that the surface is not static, but is constantly changing. In the southern hemisphere, where fewer craters are found, there are features that look like cracks. When viewed with enhanced color imaging, they stand out as bluish lines. What geologic activity could be causing these features? This was a mystery until the Cassini craft imaged the night side of the moon, when the sun is blocked from view. Cassini found volcanoes on Enceladus, not shooting out lava, but instead spraying jets of water ice into space and into the E-ring. These cryovolcanoes may be fueled by chambers of liquid water beneath the icy surface, similar to ones that hold water for geysers here on Earth. These caverns are thought to be heated by radioactive decay and by tidal forces placed on Enceladus by Saturn and nearby moons. In 2005, Cassini flew through one of the clouds and found that it also contained minute traces of molecular methane, carbon dioxide, and nitrogen, one of the core chemical elements needed for life. Could bacterial life thrive in the liquid water beneath Enceladus's surface? Today, Enceladus is the best documented out of the handful of bodies in our solar system to have volcanic activity. And although no volcanoes have yet to be found on Saturn's largest moon, Titan, it is still one of the most Earth-like worlds we've explored. Larger than our own moon and the planet Mercury, Titan is the only moon that has a dense atmosphere. Thicker than ours, it is incredibly smoggy, so much that the surface of Titan can't be seen through it in visible light. Cassini brought along the European-built Huygens probe. It landed on Titan in early 2005. This was the first time a space probe had ever landed on a surface in the outer solar system. As it traveled through Titan's atmosphere, it took measurements of atmospheric composition, recorded wind speeds, and took a series of images. These images showed signs of erosion caused by flowing liquid that fills many rivers and lakes. But this liquid is not water. It's too cold for that. Rather, it is liquid ethane and methane. This fluvial erosion can be seen in radar images of Titan's surface. Such images show diverse geology, such as dunes and lakes like these, named kissing lakes. Huygens also recorded atmospheric pressure as it descended down to Titan. When we study how the pressure changes with altitude, we see that it resembles the pattern that produces Earth's water cycle. But Titan is almost 300 degrees colder than Earth, which means that instead of water, methane condenses into clouds and rains back onto the moon. When the methane reaches the upper atmosphere, it can be broken down by sunlight. This is what produces the thick orange smog we see around the planet. This smog reflects sunlight back into space, a sort of anti-greenhouse effect, making Titan's surface colder than its upper atmosphere. Typically, small planets and moons are found to have only trace amounts of atmosphere. Any atmospheric gases are lost to space, as the planet or moon's gravity is not strong enough to hold them. Yet, despite its size, Titan's atmosphere is thicker than Earth's. Obviously, gravity is not the only deciding factor when it comes to how dense an atmosphere can be. The planet Mars, which is almost half the size of Earth and about 2 times larger than Titan, has an atmosphere 100 times thinner than our own. Here on Earth, our atmosphere is protected by our magnetosphere, which is created by magnetic fields. Without it, gases would be stripped away by solar wind, streams of charged particles from the sun. Such was the case for Mars. Titan orbits inside Saturn's magnetosphere, the second strongest in the solar system after Jupiter's. This helps to protect Titan's atmosphere from solar winds. It took over 300 years after the discovery of Saturn's rings to find that other gas giant planets in our solar system also have ring systems. Faint rings around Uranus were discovered by the Kuiper Airborne Observatory in 1977. Jupiter's had to wait until it was visited by Voyager 1 in 1979 before they were discovered. Neptune's rings were not verified to exist until Voyager 2 imaged them about 10 years later. What about planets outside of our solar system, planets that orbit other stars? Such planets are called extrasolar planets, or exoplanets. It is the job of the Kepler Space Telescope to find them. Kepler points towards a region in the sky called the Summer Triangle. This triangle is marked by 3 bright stars: Deneb, Vega, and Altair. Aimed between Deneb and Vega, Kepler has found hundreds of exoplanets. Kepler continuously monitors the brightness of 150,000 stars. Any exoplanets are too small and dim to be seen, but if their orbits carry them in front of their host star, Kepler will see the star dim. By measuring how much light is blocked, we can determine the size of the exoplanet. Kepler has found many giant exoplanets with densities that suggest they are made of gas, similar to the planets known to have rings in our own solar system. Because these gas giants are often found close to their host star, exoplanets proposed to have rings are called warm Saturns. Icy rings would likely melt in this location of immense heat. The rings may therefore be composed of rock. Using another method of exoplanet detection, we can determine the planet's mass. Along with its size, its density can be calculated. How can this help us detect rings from Earth? We saw that the rings, if tilted in the right way, can block starlight, just as planets do during transits. This extra blocking of light could make the planet appear to be 10 times larger than it actually is. This would give a density value less than the actual density of the planet. Exoplanets found with very low densities could be a sign that the planet has a ring system. Late this evening, the Big Dipper can be found high in the north. We can follow the arc-shaped handle to the red giant star Arcturus. When we follow it farther, we reach the bright star Spica. Located just to the east of Spica is the planet Saturn. For now, we have it to study while we try to find the answers to the mysteries of the universe. Cassini has provided views of Saturn, its rings, and its moons with clarity far exceeding that of the Hubble Space Telescope. With Cassini, we are seeing more than we ever thought possible. We truly have come a long way since Galileo's first drawings of Saturn.